Project 3.6 ISP Medium Blender. The completion of this project centers around the development of a compact Arduino-controlled blender system that integrates mechanical design, embedded control, and electromechanical actuation. The wiring of the system establishes the physical foundation for all electronic interactions within the blender. The Nano was mounted on a perma-proto board, serving as the central controller and distribution point for both power and signal. The top rail was used for the 9-volt power supply the motor needs, and the bottom rail was used for the 5-volt rail for the Nano. Input buttons were connected to digital pins 9, 8, 7, and 6, providing a distinct user command, including direct motor activation, time increments, time decrements, and timed operation. These inputs were configured as digital signals, allowing the microcontroller to continuously monitor their states. Because the Arduino Nano cannot supply sufficient current to directly drive a DC motor, a transistor-based switching configuration was implemented. Additional integration was achieved through the inclusion of an I2C liquid crystal display. The serial communication method significantly reduces the number of required connections, allowing the display to be incorporated without overcrowding the limited pin availability of the Nano. The LCD provided real-time system feedback, including motor state and selected timing values. The software component of the project was designed to translate user inputs into precise control actions while maintaining continuous feedback through both the serial monitor and LCD interface. While the setup function, all inputs and output pins were configured, serial communication was initialized, and the LCD was prepared for operation. The main loop of the program continuously evaluates the state of each input button. When the primary control button is pressed, the motor control pin is driven high, activating the transistor and allowing current to flow through the motor. The result in immediate motor operation with corresponding feedback displayed on the LCD. When the button is released, the motor is turned off. Additional functionality is implemented through the increment and decrement inputs, which adjust the timing variable in 0.5 second intervals. Each change updates both the serial output of the LCD display, providing immediate visual confirmation of the selected duration. This variable serves as the basis for timed operation mode, in which pressing the designated button initiates a complete blending cycle. The overall design of the blender system reflects the integration of mechanical precision and electronic control in a cohesive electromechanical device. The enclosure and structural components were designed in Fusion 360, with particular attention given to alignments, clearances, and sealings. The use of coil tool allowed for the creation of fully modeled threads, enabling a secure and watertight connection between the body and cap. This was essential for safely containing liquids during operations while maintaining ease of assembly and disassembly. Using these tools, a threaded cap and main blender body was designated to house all components of the system within 3 distinct interlocking parts, ensuring proper alignment and cohesive overall assembly. This concludes Project 3.6 Medium ISP Blender.